In previous chemistry courses, you have probably looked at the Lewis structure for bonding in passing, but we're going to look at it a lot more in depth in AP Chemistry. So let's look at a few practice problems. This first one, we have a diatomic molecule. And we'll always start by drawing our Lewis structure for each atom. We know that nitrogen has 5 valence electrons. You can arrange them however you want. We need to count the total number of electrons. 5 plus 5 is 10. So we know that at the end we should have 10 electrons. Because it's neutral, we don't add anything. And we have to satisfy the octet rule for all of them. All of these examples will obey the octet rule. Makes them a little easier. So we can probably see that these are going to share, as are those two. With these simpler forms, it's always going to be the unshared electrons involved. You always will try that first. We can simplify this drawing by replacing those circles with nice neat lines. We can count a total. Remember, each line represents 2 shared electrons, so 2, 4, 6, 7, 8, 9, 10. We still have 10 electrons. And each nitrogen has 2, 4, 6, 8 electrons around it. So this is what that bond looks like. Let's look at B. Whenever there are 2 different types of atoms, you have to decide who's in the center. If there's one atom that there's only one of, like this case carbon, there's 1 carbon and 4 fluorines, that carbon is going to be the central atom. In our example D, where we have 1 nitrogen and 2 oxygens, the nitrogen is going to be your central atom. So that's a good rule of thumb. We know that carbon has 4 valence electrons, and it is special because it does not obey the typical rule for how we draw these. They get all spread out. Fluorine has 7. I'm going to draw these to make this bonding a little easier to show. But you can draw that however you want. You can make a list. As long as after you draw your crazy sharing circles, you clean it up and show me the nice neat lines too. So we need to count our electrons. We have 4 electrons that have 7, so that's 28, plus carbon has 4. So we have 32 electrons. When looking at this, you can probably see pretty quickly that these unshared ones match up, these lone pairs. And we create a molecule that looks like this. This drawing is not correct. You have to show the unshared pairs for me. So we can see that this fluorine has 8 electrons. 2, 4, 6, 8. As does this one. And this. And this. We can count for our carbon, 2, 4, 6, 8. That's also satisfied. And if we count our total number of electrons, we have 8, 16, 24, 32. So we have the same number of electrons. We know that we are done with our drawing because we have satisfied the octet rule for everybody, and we have the same number of electrons as we started with. Let's look at one more of these fairly simple examples. One nice thing about hydrogen is you know that it is always the terminal atom. Because it has 1 electron, it cannot bond with more than 1 atom. It has to be on the end. So this is a very basic one, but I wanted to show it for one reason only. Hydrogen and helium do not follow the octet rule. Because they only have that one s orbital, they can be completely satisfied with 2 electrons. So instead of counting for 8, we can see each hydrogen has 2. We know that we started with 1, 2, 3, 4, 5, 6, 7, 8 electrons total. And that we have also ended with 8 electrons. We do not show any unshared pairs because hydrogen does not have unshared pairs. Each line represents 2. So I only showed this example to help you remember that hydrogen and helium, which we won't be dealing with because it's a noble gas and it very, very rarely does anything, will only need 2 electrons. Let's look at these slightly more difficult ones where we have charges. Let's start by looking at problem D. So this molecule has a negative charge, which means we have 1 additional electron. So let's draw our Lewis structures. We know that nitrogen is our central atom. We know oxygen has 6 valence electrons. And we know we've got 1 extra electron. And I'll just draw it out over there. What happens is these unshared match up, and so do these. And that gives us a nice little hole for our 1 extra electron. To clean this up, we have a double bond with this oxygen. Now for this, it does not matter which side you put the oxygen on. That's not resonance, that's just, it's symmetrical. So it's the same compound no matter how you write it. To show the charge that we have 1 extra electron, we do it like this. Let's count our electrons, which I've neglected to do. We had 6, 12, 17, 18, because we had our 1 extra. 1, 2, 3, 4, 6, 8, 10, 12, 14, 16, 18. And if you count, each atom has satisfied the octet rule. So we know that we are complete with that. Let's look at E. Because honestly, if NO2 -1 works, it seems to me surprising that we can add an extra oxygen and it just works out as well. Let's start with our nitrogen because we know it will be central. And we'll work on our oxygen. And we have 1 extra electron out here. If we count, we have 6, 18, 23, 24 electrons with our 1 extra one. We can do the easy parts first. And we can say, hey, this extra electron is going to go right there. So now we have 2 atoms satisfied, and we have this. And you might think, oh, well then they're just going to bond with each other. But we're not going to make a ring like that. That is not stable at all. Instead, what's going to happen is this electron is going to travel over here. So now this guy's satisfied. This one only has 6. So nitrogen is going to be a nice guy and share his unshared pair. So all of this notation is to help us figure it out. The important part is how we draw it afterwards. We have our nitrogen, single bonded to this oxygen that has 3 unshared pairs, 2, 4, 6, 8. That oxygen is happy. Single bonded to this oxygen that also, with the addition of that one, has 6 unshared electrons for a total of 8. Now this oxygen has a double bond because of that unshared pair being shared. And only 2 unshared pairs, but still 2, 4, 6, 8. Our nitrogen, 2, 4, 6, 8. Everybody's happy. If we show that to show that we have a -1 charge, this is what that compound looks like. Now this compound does have resonance structures because that double bond could just as easily have been here. But we will talk about resonance later in the chapter, so don't worry if that doesn't make sense to you yet. In fact, we'll use this exact example later in the chapter. Let's look at this final example for F. This one's a little bit different. We have a positive charge, which means we have lost an electron. Our nitrogen has 5. And we have 4 hydrogen atoms. 3 makes sense. Ammonia, super easy to draw. You can see where those pairs come in. This one's a little bit different. If we count our electrons, we have 5, we have 9, but if we're going to lose one, our final one must have 8. So to talk about what really happens here, let's do the easy bonds first. And this hydrogen loses its electron. It's gone. It's got nothing. What happens is this very positive hydrogen is attracted to these very negative unshared pairs and gets shared that way. We end up with nitrogen surrounded by hydrogen, thus satisfying the octet rule and giving the duet rule for hydrogen. And as long as we show the charge, showing that we lost that 1 electron, this is what that structure looks like. So you should be able to draw the more basic ones. There are situations that don't follow the octet rule, and those are the examples we're going to do next.